Thanks, Fred, for the invitation, and thank you very much for holding up and waiting for my talk. Some fascinating work has been discussed. I would like to extend that a little bit if I can, and I will be interested in talking to you some of the sovereign technology that we are developing in Australia, and hopefully with the aim of making two things. One is transforming our red bin into a yellow bin, so that's one thing. The second thing is making Australia a global plastic recycling hub. So those are the two main goals that we have. And so my research spans a lot of different fields, and I'll be talking a little bit about it. But today I'm going to focus predominantly about this new invention that we had. And this was just before COVID, we started this research, which is now giving fruits now. All right, so little bit of background about me. So I was born in a very small town on the foothills of Himalayas in India, next to the river Ganges. Very beautiful back in the day, not anymore with climate change. So I did my undergraduate degree in the capital of the country in India, did my honors in chemistry. Then I moved to Australia 17 years ago to do my master's in chemistry at University of Tasmania. Did my PhD in Perth. At GWA, and Mark was talking about spray-on skin, so one of my supervisors was Fiona Wood, and then did my postdoc at the Indian Institute of Science, and then I moved back to Australia in 2018, and then got promoted to senior lecturer. So my research field is in three main domains: polymer nanocomposite foams, polymer nanocomposite coatings, and now plastic recycling. So I'm not going to go into too much detail about these things because it's too technical. One thing I would like to highlight is how fundamental research can stem into something more applied. So while we were inventing this technology, which is on the left about three-dimensional foam, which is now patented, we came up with the idea to recycle plastic. That was just before COVID. And since that has been patented as well. So a little bit of background as well. In terms of our work, there's a range of applications that we have demonstrated. Some of them are funded by the government, some by the industry, some of it has been patented. One of the stuff about stealth coating is with Office of National Intelligence. So we are trying to build another sovereign capability for Australia, especially now, considering what is happening in the United States, we have to be more independent for our own defense. And so that is one of the capabilities that we are developing in the field of nanocomposite coatings. All right, so that is pretty much the background. I'm going to talk about polymer composites. I'm going to talk more about the plastic recycling stuff today. So Helen, before me, alluded to plastic recycling, which was great. It gave a segue for me to talk about what we are doing. So a little bit of history about plastic, how it came to being. If you would have seen this, you would realize that Goodyear, and some of you might be still using those tires, they were the first people he was the first one to realize that natural rubber can be of any use. And they started the whole process of natural rubber and into the tires. And since then, the whole revolution of what these long molecules can be used for has started, which is, as you can see, it was mid of 19th century. And there came some of the key names that you can see. So it started with polystyrene in 1840, PVC 1872, which is used in all the insulating materials in electrical wires. And then came the key things. LDPE, so that's a low-density polyethylene, and then high-density polyethylene, and you can see it took around 15 years. Some of these inventions were driven by necessity during the wars. All right, so for example, during the World War I, silk needs to be replaced because it was too difficult and too expensive to use to make ropes. And that's when nylon was discovered. All right, so moving on from 1951 when the HDPE was discovered, soon polypropylene, and then going on, there are two things you will realize in this whole cycle. One is the key date of 1931 is when the first evidence of some sort of plastic in ocean was noticed. And the second one is moving on from 1960, it has come to our attention that actually this noble, amazing material that we use and we are dependent on has started to become a problem. 2 Nobel Prizes have been given on different aspects of plastic manufacturing over the years. Now, why are we so interested in plastic? I mean, you would already use plastic every day, I'm sure. If you don't, I can tell you, yes, you do, including the buttons that you have on your shirts. They're all plastic, Bakelite. So why it's a huge thing is because commercially it's a massive market. So that's the report from 2023. The global plastic market was 623, 24, 25 billion. Do you know at that year what was the GDP of Australia? Does anybody would like to guess? What's that? So I can hear some mumbling. It was just 3 times that. So you can imagine 1/3 of Australian GDP is the global plastic market. You can appreciate how big that is. Now, if you look at just the packaging industry, you would see that 80% of that is soft plastics. Or what is soft plastic is polyethylene and polypropylene, right? And as Helen was saying before, bottle caps, which are polypropylene, cannot get recycled. So thank you very much for alluding to that point. Now, if you look at just the region that we are in, Asia Pacific, you will see that we contributed 22% of the global market. All right, so we are major contributors to this big supply chain. Now let's get honed into Australia, right? How are we doing with plastics? All right, so we are amazing. We consume a lot of plastic, right? So we consume around 3.5 million tons of plastic every year. 1 million tons of that is soft plastics, right, which cannot be recycled currently. If you look at this graph stats over there, by 2050, it is projected that we're going to have more plastic in the ocean than fish, right? So you can imagine how big this problem is becoming. And we're going to double our consumption of plastic by 2040, which is not very far. It's by the next decade. So the other thing is, in that 1 million ton of soft plastic that we use, 70 billion pieces is what they contribute to, right? So that's a huge number. Now, plastic by itself is a problem, as you would have already heard of or read about. But I'm not sure if you know or you're aware how big of a contributor it is to global greenhouse gas emissions, right? So it's a compound problem. So this is just the stats here. So this is comparing 500 megawatt coal-fired power plants, and everybody knows our current government is all about renewables, and so is the opposition. And you will see that when you're comparing those coal-fired power plants that nobody wants to support right now, we are contributing an insane amount of carbon dioxide by just using or producing plastic, right? The plastic is not just production is the problem here. It's the whole entire life cycle of it. It's the production, consumption, and then the disposal of that plastic, right? And so all of that contributes to greenhouse gas emissions. Now, you might have heard that, oh, we put stuff in the yellow bin, gets recycled. Fact check, doesn't. Most of it doesn't get recycled, right? So thank you very much for doing your job by putting into yellow bins. Hopefully soon enough, we'll be able to do it with our technology, and I will show you that. But there are different estimates and different reports from different countries. Nobody knows exact numbers, but roughly around only 13% of global plastic gets recycled. And in that is just an estimation. We don't know how much it is. Most of it goes to landfill, as you can see from this graph. Some of it gets incinerated because it's fossil fuel, so it's a very high caloric index. Some people think it's a good idea, but the amount of NOx, the sulfurous gases, nitrous gases, and carbon dioxide that is produced through the environment, jury is still out whether it's a good idea. So out of all these different types of plastics that we use, what type of plastic does get recycled a little bit is outlined in that graph on the bottom right. As you can see, there are two types of plastic you will notice that actually gets recycled. One is what is called a PET, which is what all the water bottles are made up of. The other one is HDPE, so high density polyethylene. Can you guess what is it that we use every day, most of us, if not all of us, that is made up of HDPE? Little bit in cars, not as much. How many of us like coffee here? I'm assuming most of us. The milk bottles, they're all HDPE. And those are the only things in HDPE which gets recycled. All right? There are a lot of other things which are made of HDPE does not get recycled. And I'll show you the evidence of that. So why has this become a major problem? Right? Well, the problem is this. Right? So these materials are so good that they do not break down easily. Right? We cannot do anything with them. We cannot break them down to anything. But the nature does that to us. Right? So it's natural withering process. What it does is, especially this happens predominantly in the oceans. So you have the salt and you have UV rays from the sun. What it does, it breaks down the big block into a smaller and smaller and smaller pieces. Right? Do not confuse this to breaking down the chain of the polymer. Right? So polymers are like a train, which has a lot of compartments, and those compartments are called monomers. So we are not talking about breaking down that train into smaller pieces. We are talking about just the bulk material reducing into smaller chunks. And that is what is called micro and nanoplastic. It's all over the news these days. And there's a lot of buzz going on with this, which is in a way a good thing, raising awareness. So how is that for us a major problem now? Is because of this food chain. We are very proud to be on the top of food chain, and that is the problem. So what happens is when there is microplastic and nanoplastics in the ocean, it gets consumed by the fish, and guess who consumes the fish? In addition to us, well, first of all, us, and we don't want to share it with anybody else, but there are other animals who wants to consume it too, and that's how it gets into the whole food cycle. Now I'll share some statistics with you at the bottom here. That is just published few years back, where they showed the amount of microplastics that is found in humans and children's there. This is actually fascinating and really scary. Those numbers on the y-axis, they are 50,000 pieces. That's just annual consumption. And I noticed this when I had my little one crawling on the floor mat, licking on everything. And guess what it's made up of? Nylon, right? So it's no wonder we are consuming insane amount of this stuff. And it's getting accumulated in our body because we don't have natural function of how we get processed, unlike carbon that Benjamin was talking about, where we know how to process carbon because it was when we were formed, not the plastic. So there are good alternatives you might have heard of. Again, some of them gets a lot of news. There's always a new biopolymer somebody has made. Some of them are called bioplastics or biodegradable plastics. Now, they're well and good in their own right. However, there's a big problem with bioplastics is they do not break down, unlike what is claimed. There was a report published just a few years back by the American Chemical Society, where they've shown that one of the key, biggest biopolymers in the world, it requires very specific conditions in the landfill to break down, which is difficult to, first of all, it's very difficult to achieve. Second of all, it's very expensive to achieve, right? So it's eventually going to end up in the ocean because it will not break down in the current landfill conditions. So the other problem with biodegradable plastics, there are a couple of different strategies industry has explored, other researchers have explored. They come with their own limitations. Take-home message is, if they do not break down, they cannot be recycled. Right? Let's just take that home. Now, There are few strategies. If you remember, I talked about around 13% global waste plastic gets recycled. One of the biggest way that people recycle them is called what is called mechanical recycling. Now, again, this has been very contested. Again, last year a report came from American Chemical Society saying this is not a recycling method, but nonetheless it's called mechanical recycling. So very simple process. What they do is they take, usually works with your milk bottles and your water bottles. You take those, chop them, wash them, and then use them again to make a new product. Sounds very simple, sounds very elegant, works good. Problem is, it only works on clean and clear plastics. By clear, I mean transparent plastics. It cannot work on colored plastics. Now, if you consume soft drinks or some of the fancy water bottles, you would see that they have tints of colors, if not complete colors. And those materials, those bottles, no matter how much you put them in the yellow bins, they all end up in landfill because they cannot be recycled. So the industry wants something like this. So this, the bottom right image over there, they're called plastic pellets, right? So virgin plastic, when it's made up of crude oil, eventually gets processed into that material, which is the starting material. And mechanical recycling results in the top right image, which is kind of like flaky kind of material. And they are then combined and recycled to make new products. Now, there are other methods which are listed in the bottom graph here. They have their own limitations. So there are a couple of limitations I would also like to highlight in addition to what is written here, especially in terms of mechanical recycling, because it's the biggest market in the world in the way the plastic gets recycled right now. One is, like I alluded to before, I said before, is they work on clear plastics. Second is they cannot remove any additives which are added to plastic. And you might wonder why the additives are added is because we want to change the properties for specific applications. What do I mean by that is, if you would have noticed, your soft drink bottles are hard, but some of the water bottles are scrunchy, right? So those are manipulated two different ways, predominantly. One is by changing the train length. The other way is by adding some sort of additives into the mixture, right? So those additives cannot be removed using mechanical recycling. Third of all, it's very easy, kind of what Helen was talking about, when you try to recycle a bottle, you have the O-ring and the cap. They try to remove the cap, but there is an O-ring still there, which cannot be easily separated. It all comes down to the cost. And that is made up of polypropylene. And that gets then contaminated into the PET, for example. And then that limits the time this material can be recycled. The other thing is, this process eventually leads to these materials can only be recycled few number of times. And that number is also very contested, both by industry and by academic research. So where are we going with this? It's all not doom. There is some gloom here as well. So we invented this new technology that we think can revolutionize the way plastic gets recycled globally. What we came up with is a completely new approach. We take waste, and this can be virtually any kind of waste plastic, not limited to one type of waste plastic. We process it polymer to polymer, and we make something which looks like almond milk. It's not almond milk. Don't even think about it. It's very far from almond milk. But then that can be processed and can be made into those pellet-like materials. And I'll show you all of that. And then can be made into new products. In addition to that, the advantage of making that almond milk-like product is that material can directly be used to make insulation coatings into your homes, on your walls, or can be added to concrete, for example, to again have heat insulation in your bricks and mortar. Now, how do we do it? I can't describe it to you because it's commercial in confidence, but I can show you some of the data. So we start with waste. Again, I showed you this is what we make in the middle, but that's the kind of recycled material we get. Where are we with it? That's where we are. So we have been able to scale it up. This is the 40 kilogram batch that we can make. This only takes around half a day to make, relatively cheap. So the technology works really, really well. Now, what can we do with it? We can take that material, mix it with the virgin material, and make these kind of rolls. Now, these rolls are prerequisite to make your water bottles or anything else in the industry, right? So we have demonstrated that we have the capability, this is in collaboration with our industry partner, that we can actually do all of this stuff. Now, this is all about PET, and I'm not going to get into too much about PET. Happy to answer any questions you might have, but I'm more interested in talking about soft plastics, which I right at the start said cannot be recycled, as what Helen said as well. And I would like to give you first some evidence of that that's not true. We can recycle. So here's just example for all the chemistry nerds in the group. Some of the pipettes, plastic pipettes that we use in the lab, we can recycle those. Shopping bags, we can recycle those. So some of you who are really environmentally friendly people in the group, you might have heard of RedCycle and must have taken part in the deposit schemes at the supermarkets. Guess what happened to that? They're all in the warehouse in Victoria waiting for fire to occur, right? Super risky because, like I said, they're just crude oil, basically, right? So very high caloric index, very dangerous. Can catch fire at any time. But we can recycle those. Here you go, polypropylene, the bottle cap, what Helen was alluding to. We can make these balls or particles, as we like to call them, which are pellet-like material, directly from those different waste. People who like hair gels, there you go, we can recycle those bottles as well. This is what these particles look like under the electron microscope. They have a rough surface, spherical, nothing very exciting about it. I just wanted to show you if somebody wants to be interested in knowing how they look on the surface. This is the golden slide where I would like to take to you. Very new. I mean, we have been showing this. This is the first time we have demonstrated in a mixed waste. So I was asked this question some time back. It's all well and good you can process one polymer or one plastic or one type of waste at a time, but can you do it on a curbside real waste mixed plastic? Here you go, the evidence. That's some of the waste that we collect in my home, because apparently nobody in my group has any waste. So I was forced to do this, so I did. The bottom graph here, without getting into too much detail, is what is called a DSC curve, what is called a differential scanning calorimetry curve. What it shows is two things. One is called a glass transition temperature. I'm not going to get into details. But the important thing, which is the bottom bit where I put the name of the polymers there, is what is called a melting peak, where that polymer actually melts. That melting peak is very signature of a type of polymer. So we can identify, we can also quantitate the amount of that polymer that we have in our mixture. So what do we have from all this mixed waste? There are three that I've listed here. We have low density polyethylene, high density polyethylene. We have polypropylene to some extent, that's a small bit. We also had aluminum here, and we also had PET, right? So these wrappers can contain any type of waste plus mixed waste. So what can we do with it? We can actually, in our process, isolate different polymers in situ in the process itself. So we do not have to start with the segregated waste, which is one of the requirements for mechanical recycling, like I said before. So we can take any mixed waste and isolate them in situ, separate them out, and recycle them. And here's the evidence. So from this, we took LDPE fraction out. This is what it looks like. Colored. So starting from different colors, we get some sort of a mixed, not a very good looking color. Then after that, we separated our HDPE out, so which is high density polyethylene, which is another second major phase. And then we also isolated polypropylene. I'm not showing data for PET because there was very small amount. And obviously aluminum, this is plastic recycling, not aluminum recycling. So we don't show that here. So we can isolate all different polymers, right, in situ in this process itself. Now this is at scale, right? So now we have reached to hundreds of gram scale where we can show that it actually works. And this is what it looks like when we remove the dye. So you might have thought, yeah, it's well and good. You can do something with it. Can it be used for something? So when I said at the start, industry needs clear waste, they start with clear waste because they need to make clear material. So they need to remove the dye, which they cannot right now, but we can in our process. So some of the key advantages, we are not using any high temperatures or high processing energy parameters. Therefore, we are very comparable. We can isolate the polymers in situ, which is the biggest advantage that any process to date has ever developed can do. We can deal, I'm not showing the data here, but we have shown that we retain the properties of those trains. So we do not break down the length of that train, the polymer chains. And we retain, therefore, intrinsic properties of these polymers. Those are really important for industries because they need specific properties to make specific material. So what can make a water bottle, that material cannot make, say, a punnet, right? So they need very specific properties, and that needs to be retained when you recycle materials, which we can. So why are we interested in this, and how we think that this can actually revolutionize and make Australia the recycling hub, global recycling hub, is because of the stats here. So 2024, this is just the recycling waste plastic market. It's around $45 billion. We contribute very little to this, obviously because we are a small country. But we have the potential to really achieve something that nobody else has and capture that market when it's going up. So with that, just the acknowledgement of my team members. The ones in the blue are the ones whose work I've shown predominantly today, and my collaborator, who is the co-inventor with me in the technology. And that's it. Thank you very much for your attention.